Hey guys, today we're doing Chapter 9, Section 7, which is on the fundamental theorem of algebra. So the fundamental theorem of algebra is basically what we can use to determine the nature of roots of a polynomial function. So we're going to start off with our discriminant theorem for quadratics, which you learned in advanced algebra. Basically what that says is when your discriminant is a positive number, then we'll have two real solutions. When your discriminant equals 0, you'll have one real solution. And when your discriminant is a negative number, that gives you two complex solutions. And we know that's true because our discriminant is just b squared minus 4ac, which is the part that's underneath the radical sign in your quadratic formula. So if you have a negative number underneath your quadratic, or underneath your radical sign, then that's just going to give you an imaginary number, which is why you have two complex solutions. Alright, so some history on the fundamental theorem of algebra. Mathematicians were not satisfied only being able to know this for quadratics, so they searched for ways to prove how many zeros a function can have for higher degree polynomials. By 1797, Gauss, when he was 18, proved the fundamental theorem of algebra. That's right, he was only 18 years old when he proved that. So if p of x is any polynomial of degree n greater than or equal to 1 with complex coefficients, then p of x equals 0 has at least one complex solution. Note that real and imaginary numbers fall beneath the complex numbers on the hierarchy. Thus, they both apply to this theorem. So in essence, all zeros of a polynomial are complex zeros. This theorem leads to a less abstract result. We can say that a polynomial of degree n has at most n zeros. So notice that says at most. So if I have something like a 7th degree polynomial, that means that at most I could have 7 zeros, but I could have less because some of those could be imaginary. So example 1, let's find the zeros of p of x equals x cubed minus 6x squared plus 9x. By only looking at the equation, what is the most amount of zeros it could have? Well, looking at this equation here, I see that the highest power is 3, or the degree of the function is 3. So that means that the most zeros that I could have is 3. Alright, we've got our number of zeros of a polynomial theorem. That says a polynomial of degree n greater than or equal to 1 with complex coefficients has exactly n complex zeros if multiplicities are counted. So real quick, let's talk about a multiplicity. Essentially, a multiplicity is just saying that your zero is counted more than once. So for example, if you have an equation like, let's just say, x plus 3 squared. Well, I know that if I factor that out, it's already basically in factored form. It's just x plus 3 times x plus 3. So if I used my zero product property and found the zeros of that, I would get negative 3 twice. Well, on the graph, I'm only going to see that 0 once. It's going to cross through negative 3, and that's it. So a multiplicity is just saying that in your function, there's more than one of those zeros, whereas in your graph, you can only see that one zero. So if multiplicities are counted, we have exactly n complex zeros. So if I have a 7 degree power, then I'll have exactly 7 zeros. Now some of them might be imaginary, some of them might be multiplicities, but I'll have exactly that many. Multiplicities are when you have the same factor multiple times in an equation. For example, p of x equals x minus 3 times x minus 3. The factor x minus 3 is there twice, so it has a multiplicity of 2. Okay? If it was there 3 times, it would have a multiplicity of 3, etc., etc. So let's do this better and not just worry about zeros. We've got this theorem here that says let p of x be a polynomial of degree n greater than or equal to 1 with real coefficients. The graph of p of x can cross any horizontal line y equals d at most n times. So this theorem is important because if you're only given a graph and you need to come up with an equation, in order to figure out the power of the equation, you can actually look at how many times it would cross any horizontal line. So you're looking for the maximum number of times that it would cross a horizontal line. So looking at this graph here, I want to think about what is the maximum number of times that this would cross a horizontal line. So let's just try drawing in a few horizontal lines. If I drew in a horizontal line here, it would only cross in 2 spots. Okay, is that the maximum number of places it could cross? No. What about down here? Again, this would only cross in 2 spots. So I need to look for places where it could cross in the most amount of spots. Well, if I draw a line right here, I'm crossing in 1, 2, 3, 4 spots. I personally can't see another place where it could cross in more spots than that, so I'm going to say the minimum degree of this polynomial is 4. Notice that I said minimum, because remember that in a graph, you could have complex zeros that aren't being represented or multiplicities that aren't being represented. So the absolute bare minimum degree of this function would be 4, because it's obviously going to cross in 4 spots. Alright, we've got our conjugate zeros theorem now, and that says let p of x equal a sub n x to the n, blah, 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 so some sort of polynomial function where a sub n minus 1, etc., those are real number coefficients. Our leading coefficient is not equal to 0. If z equals a plus bi is a 0 of p of x, then the complex conjugate of z, a minus bi, is also a 0. So what this theorem is telling us is that whenever you have a complex 0, you also have a conjugate of that complex 0. And the reason we know this is because if we think about our quadratic formula, it's negative b plus or minus, right? So it's plus or minus that b squared minus 4ac underneath the radical. So that plus or minus right there is basically representing the original complex solution and the conjugate of that complex solution. So complex zeros always come in pairs, and they're always conjugates of each other. So if you know one complex zero, you automatically know that there's another one. Alright, there's an example of a problem like this in your textbook, but let's just go through it. So the first one says verify that I is a 0 of p of x. So this is my function p of x, x to the 4th plus 2x cubed plus 11x squared plus 2x plus 10. If I want to verify that I is a 0, well, I know that using the theorems in the previous chapter, if f of c equals 0, that means that it is a 0 of the function. So basically, if I plug this into the function for x, I should realize that it's a 0. I should get no remainder also. So I to the 4th plus 2 times I cubed plus 11 times I squared plus 2 times I plus 10. I'm going to solve this out. So I to the 4th, I know that that's just 1. I cubed, remember that I cubed is negative I. So this is minus 2I. Okay, I squared, remember that's negative 1, so this would be minus 11. This is plus 2I, and this is plus 10. So I've got negative 2I and positive 2I. Those are going to cancel out. I've got 1 plus 10, that's 11, minus 11. This gives me 0. I've just verified that I is a 0 of this function. So now I want to find the remaining zeros of p of x. Well, this is where your complex conjugates theorem is going to come into play, because I already know that I is a solution to this equation. Therefore, I know that the complex conjugate of I, which would be negative I, is also going to be a 0. So if I know that I and negative I are both zeros of this function, I can write those as factors. So as factors, this would be x minus I and x plus I. So if I want to factor those out of that function, it'd be easier if I factored them out both at the same time. So what I'm going to do is I'm going to multiply these together. So I'm going to FOIL. I get x squared minus xi plus xi, and I times I, that's negative I squared. When I simplify that down, negative xi and xi, those cancel. negative I squared, that's plus 1. So this is x squared plus 1. So now what I'm going to do is I'm going to divide my original polynomial by x squared plus 1. And make sure you put in your placeholders. So this is x squared plus 0x plus 1. And I'm dividing x to the 4th plus 2x cubed plus 11x squared plus 2x plus 10. So to get from here to here, I multiply by x squared. Then when I multiply this all through, I get x to the 4th plus 0x cubed plus x squared. And I subtract. This gives me 2x cubed plus 10x squared. I can bring this one down. To get from here to here, I need a 2x. And when I multiply this through, I get 2x cubed plus 0x squared plus 2x. And I subtract. So I get 10x squared plus 0x plus 10. So to get from here to here, I need a 10. And when I multiply that through, I get 10x squared plus 0x plus 10, which gives me a remainder of 0. So now I have x squared plus 1 times x squared plus 2x plus 10. So now I can factor this equation, and I'm going to do that using the x game. So I know I'm looking for two numbers that add to 2 and multiply to 10. Okay, so with 10, I've got 10 and 1 or 5 and 2. Neither of those work. So, since my x game doesn't work, what I can do, because I just want to find the zeros, I don't actually want to put it in factored form. So what I can do is I can find the zeros using the quadratic formula. So this, I'm going to do negative b plus or minus radical b squared minus 4ac over 2a. When I simplify that down, I've got negative 2 plus or minus, this is 4 minus 40, so that gives me negative 36 over 2. Well, the square root of negative 36, I know that's just 6i. So this is negative 2 plus or minus 6i over 2. And then I can simplify both of those to get negative 1 plus or minus 3i. So, listing out all of my zeros, I have I, negative 1 plus 3i, and negative 1 minus 3i. So those are all the zeros of my polynomial function. And that's everything for section 7.